So I guess at some point in the last 2 years, we all had fun with the Make It More trend. So someone asked to make this beautiful Swiss scenery more Swiss. And of course, GPT added some flags, it added some beautiful mountains and lakes. That's totally reasonable. But then in a later stage, it added this giant cheese tower in the middle of a market square. And that definitely violates all Swiss standards with respect to durability and precision. So just stacking Gruyere is not durable enough. But I guess we would all agree that in this specific example, it's kind of funny to see how this vision language models incorporates its biases and stereotypes. But there are some other cases where it's truly harmful, such as, for example, when GPT favors a CV just because of a certain name printed on top of it. This is one of many studies that document social biases in vision language models, and a common approach is to measure input-output bias by prompting the model, such as show me a CEO, and then analyzing the demographics of the image outputs. However, a problem with this approach is that bias categories are hard to generalize. So we were asking, are there generalizable ways in which people categorize each other? And social psychology has an answer to this question. So there is the famous paper that states that there are universal dimensions of social cognition, and these dimensions are warmth and competence. So in this paper, we were asking, can these fundamental dimensions of human cognition also help us to understand social perception in vision language models? So in this project, we measure social perception of human faces in a vision language model. The model we look at is CLIP. CLIP connects images and text while calculating the cosine similarity in its shared embedding space, and we use this metric also to measure bias. For the image prompts, we make use of two commonly used datasets, specifically UDK face and fair face, but we additionally draw upon a third dataset introduced by Liang and colleagues. We call it causal face. And you already see that the image dataset offers much more control. And this is because this is a gun-generated image dataset. So the authors put a random seed in a gun and expand upon it with respect to several directions, such as age, gender, and race. And they do so for several pseudo-identities. So this would be one pseudo-identity, and this would be another pseudo-identity, and overall they do this for 100 pseudo-identities. We refer to these three variables as legally protected variables, but a nice feature of the dataset is that they also vary what we call non-protected variables, specifically smiling, lighting, and pose. The text prompts we generate in a theory-driven way. So we draw upon two commonly used theories in social psychology. One introduces warmth and competence as the primarily dimensions across which humans stereotype each other. So a surgeon is, for example, often perceived as being very competent, but not being so warm, not so friendly, not so likable. Another model introduces three dimensions and additionally looks at different valences per dimension. But what both models have in common is that all of these dimensions are characterized by a set of psychometrically validated adjectives, such as friendly and unfriendly for the communion dimension. And it's these psychometrically validated adjectives that we enrich our text prompts with. We also vary several prompt templates and average over them in order to increase the stability of our results. So in a nutshell, first we deploy on an experimental dataset in order to draw causal conclusions. Second, we deploy theories of social perception in order to investigate generalizable categories. And third, we investigate the embedding space directly. So remember that causal phase varies legally protected, but also non-protected variables. So one question we were asking was, how do those two categories compare to each other? So what we did is that we were bootstrapping differences. So we would always sample two images, then calculate the difference in their cosine similarities, and by that calculate a distribution of differences. And then what we saw is that seed variations, so these different pseudo-identities, introduce the largest variation in cosine similarities, which totally makes sense, right? Different people are perceived very differently by CLIP. This is closely followed by race, which was also not surprising, but what was kind of surprising is to see that gender, a legally protected variable, does not introduce more variation than facial expression. And similarly, age did not introduce more variation than pose and lighting, despite being a legally protected variable. So what we conclude from this plot is that it non-protected attributes and protected attributes introduce similar amount of variation. So it is important to consider a wide spectrum of variables in order to measure bias comprehensively. And causal phase, this experimental data set, is really unique in providing the necessary level of control. Another question we asked was, how do facial expressions influence social perception? So remember, we have different facial expressions for all intersecting groups. And here we plot the facial expressions on the x-axis, and we were interested in how a non-valenced and neutral text prompt compares here. So a photo of a person the text prompt doesn't have a valenced item. And what we see is that there is already a slope with respect to the social perception. And this is exactly what we were not interested in, right? We were interested in how those valenced text prompts would perform. So what we did is that we set this neutral text prompt as a baseline and then calculated the valenced text prompts, such as a photo of a progressive person, always as a difference to this baseline. And what we see for the positive valence dimensions, positive agency, warmth, and competence, is a clear trend, an increase in slope, meaning that the more a person smiles, the more warm, the more competent it is perceived. And this is actually super interesting because it shows us that CLIP demonstrates human-like social perception. It not only can make broad associations, such as identifying different races and genders, but it also shows this fine-grained social judgment. Another question we asked was, do age-related social perceptions vary across different social groups? So remember, we have different ages, again, for all of our intersecting groups. And here we look at the agency dimension for all of our different intersections. And what we see for UTK phase, one of the two well-collected data sets, is that those intersecting groups, the gray covariance area ellipses, they largely overlap, meaning that CLIP cannot distinguish across the different groups. And a similar picture emerges for fair phase. However, suddenly when we look at causal phase, this image transforms. So now these covariance area ellipses move apart and become distinct clusters. And we think this is because causal phase allows us for a unique level of control. Upon a closer look, what we see is that there is this almost perfect ordering with respect to age, from youngest to the oldest identity for several groups. And when we transform this representation, we see that most intersecting groups kind of behave similar, with exception of one group. So there is suddenly this U-shape, and this one group are Black women. And this is not an outlier behavior for positive agency, but this behavior repeats for the dimensions of warmth and positive communion. So currently we looked at age perception in causal phase, but we can also look at how does this age-related social perception differ across the three data sets that we look at. And what we see is that this U-shaped behavior, it does not repeat across fair phase and UTK phase. And actually, we were not surprised by that because, remember, we already saw that with these phase images, CLIP couldn't even distinguish between the different intersecting groups. And most likely, this is because there is uncontrolled noise or uncontrolled variation in these data sets. So what we conclude here is that uncontrolled attributes in wild-collected data sets can mask some interesting and important phenomena to detect. Of course, our study is not without limitations. So, for example, some attributes might be more or less effectively manipulated. Liang and colleagues, the authors of causal phase, of course, controlled for this. So they had a variety of human annotators. But of course, those annotations are never perfect. Second, there might be some potential residual confounds. For example, we manually had to correct a correlation between increased smiling and brightness of the image. Our results still hold, but we can never be sure that there is no residual confound. And third, we cannot distinguish between dataset and model bias because we only look at one CLIP model. So to conclude, ignoring unprotected attributes might lead to incorrect conclusions. Second, bias patterns in wild-collected datasets remain hidden due to noise. Therefore, using an experimental dataset is extremely important. And third, this combination of using an experimental dataset with a theory-driven approach to construct text prompts enable for the discovery of important and new phenomena. Thank you, and I'm looking forward to your questions.